Hi class, it's Bill and we're back with another video in our week 6 of our Java 2 class. This is the third video in the week material about talking about trees, and we had one video introducing the concepts and the basic ideas, and we had another video that talked about x equals change x. If you haven't watched those two videos, I recommend you go back and pick those up first, and then the stuff that we're going to talk about today will make a lot more sense. So we're going to jump in now and talk about how to create the actual tree and the nodes that go along with it, and also look at some basic methods that are pretty standard and necessary for trees, and how the recursive work there makes some sense, and the elegance of it will hopefully start popping out as we go. So we are here talking about tree creation. So what do you have to do to make a tree work? Well, the first thing you need is a node. So let's look at our code here. Notice I haven't made it an external node class because why? Well, because nobody needs to speak to me in node language. They need to speak to me in data language, and it's none of their business how I store it. So notice when I act as a collection, like a binary tree, binary search tree would be more appropriate here, then I don't necessarily expose that as a separate class. Instead, what I do here is, I'll bring this over for you, and you notice down here I have my node class, and it's down here, it's actually marked private. I can use it inside my binary search tree, but otherwise nobody else can get to it. Also, I've marked it static, so if you watch the video on statics, you'll see why that makes sense, and then go back and pick that up if you haven't, and you hopefully will see that. Now, what do you have to make this go? Well, a node needs to have data. In this case, we're making a tree that just focuses on integers. Yes, in the long run, we're going to want to use generics or type parameters, but for now, let's just get the tree idea down, and then we'll move over to that in another time. So you need some way to store data. In this case, it's an integer. In the generic case, that's going to be some other type, but fine. And then you need left and right references. Those references are going to be the same data type as this. So the binary tree node here and those two here are going to be the same, right? These are going to be references to its children, and the children are the same data type. So much like a linked list where we had a next pointer that was of the same data type as the node, here we're going to have our left and right children. What else do you need to do? Well, you need to have a constructor. In this case, pass me a value, and I will make my node. I will create the node. I will put the data in there from the node value, and then I'll set the left and right children to null. You might find reason to have other constructors later, but that's certainly a fine start. Also, in this case, I'll make a very simple toString that just kind of splats out the data, just in case we want to use it in our tree. That's all we need to do to set it up. First is get the node class working. So I have that, it's internal to my binary search tree, and then I just need a couple other things. Here's my binary search tree class. I need a root reference. The root reference is, again, of type binary tree node. It's a reference to a node. And notice that, again, like with the linked list, front or list or head is not an actual node, it's a reference to a node, and so we know that special casing was discussed there, but we'll get to that later. Here we just need a reference to the root node and a constructor that sets that to null. Great. So that's all that we really need here, is to just set up the very basic thing. You need to have a node, you need to have a root pointer that points to that first node. So that's really the setup here. What else do we need to talk about here? What are some of the key methods that we want? Once we get a couple of these understood, then we'll be able to write others recursively. So we'll spend especially a little more time on add. Add is going to be our first one that uses recursion pretty heavily. This does use the x change x concept, so we'll definitely want to make sure that we're paying attention to that. And then we'll talk about some other ones. Load from file becomes trivial, and then contains will make some sense, and get data list. All those things will make a lot of sense to us. The other thing to remember is when we write recursion, we very often create two methods. We create a front end, which will serve as the client code interface. Simpler, fewer parameters, and then we'll often have a private helper function that does the actual recursion. It'll have more parameters, but that's the inside of the sausage factory that we don't necessarily want client code to be exposed to. So let's first talk about the algorithm behind add, and then once we understand it, we'll talk about the pseudocode, then we'll go look at the code, and then we'll do some other fun things with these other methods. So let's say that we are trying to come up with a way to add data to a tree. Let's start with an existing tree, and then we'll kind of work our way back into other kinds. So what do we have to do if we, let's say, want to add the number 1? Right? If we want to add the number 1, what do we have to do? Well, first of all, remember that we're going to have this root pointer, and the root pointer is always going to point to this first node. So we're always going to start there with our search. So the first thing that we're going to see, to say here in our algorithm is this thing null? Is the thing we're pointing to, because remember we're going to always start here, so is the thing we're pointing to null? The answer is no. The next question is the thing that we're trying to add less than this or not? It's not null, so we know there's a node here. Is it less than this or is it not? If it's less than this, we must then continue our search to the left, right? Continue on the left child. And again, that is a pointer, right? That's another reference to over here. And we again say, is this null? Because if it were, then we know that we need to do something different, but it's not, so we continue. Then we compare 1 to 3 and we say, hey, it again needs to move to the left, right? So we move to the left and we try that, and again that's another reference. So we follow that reference, which in this case that reference points to a null. I'll put 2 slashes to represent that. So now we have traversed and we have followed this pointer and we see that it's null. So with the add algorithm, if we ever run out of road, that's my way of saying, if you run into a place where you've hit a null, you know that that's where the thing goes. Wherever you hit a null, you know that's the right spot. So in this case, we know we need to add 1 right here. So if I erase all this ink, I know now that I need to make a new box down here. All right, I make a new node, I put the 1 in it, and of course that's going to be the left child of this thing. Okay, so that makes sense. Hopefully that makes sense to you. If we try 5, we'll start here, not null. We need to go to the left. We follow the left, not null. Now we need to go to the right, it is null, so therefore we know the 5 needs to go here, right? So the node for 5 would go down here. 12, we'd go here, not null, go to the right, go here, not null, go to the right. Less than, not null, right? Less than 17, so we know the 12 would end up down here. And 19, of course, would go not null to the right, not null to the right, not null to the right, null, so the 19 would end up down here. So hopefully all those make sense in terms of traversing. Notice that our base case for our recursion is if we run out of road, if we hit a null. We hit that because of some valid searching. We came down the right path, right? Everything was good, but we ran out of road, so therefore we know the new node needs to go here. Does that make sense? Now, does this work for an empty tree? Let's say that we just had the root reference and it pointed to something, but that was null instead of pointing to 8. Does this still work? What if I go to add 1? Well, I follow the root reference, I hit a null, I've run out of road, and I know the 1 goes here. So sure, if this were an empty tree, then the 1 would go here, that would be the root. Now just remember, based on x change x, that root now points to something new, correct? If I have, in this empty case, right, let's scratch out all this. In this empty case, this is null. I have to add the 1 here. Then root needs to repoint to it. So this is why we spent so much time talking about x change x, because a lot of times when you have finished your add, you have changed what the reference needs to point to, and x equals change x is the only easy way to fix that. So as long as we remember that, then this algorithm does in fact work for all of these cases. We just need to remember that in all of these cases, it is possible that the thing that you followed, you have to sort of think of moving up one more level back and repointing it, and x change x is what's going to let us do that. That's going to be in the previous call, and it's going to solve that problem. So let's look now at the specific pseudocode, getting a little more specific, then we'll look at the actual code. So what do we need to do? First, we need to understand that the parameters to the recursive method are going to be the data that's going to be used for the node. Makes sense, right? That's passed along from the public client-facing one. We're going to then have a start node. Why? Because we're always starting at a specific point in the tree, and as we recurse, we're going to be moving into a different spot in the tree. So we have to have some way to remember where to start. And what's going to be returned? The start node. Why? Because of x change x. Because start node may be pointed to something different, so therefore we must return it, and therefore the caller must make use of it, must remap it. Okay, so now that we've got that, what's our first base case here? Our base case is if the thing that we were passed is null. Notice that we don't try to dereference it, we don't try to use its data, we just check if it's null. So we have literally run into null. We have followed the null reference. We have followed it in and found out that it is null, and if that's the case, we create the new node and we point start node to it. Of course, at the end, we return start node. We just recognize it might be different, right? We might have remapped the local copy, which is why we have to return it, which is why we have to use x change x. Okay. What's the next case? That's our base case. What's our first recursive case? If the data that was passed to us is smaller than our data, then we need to follow the left, right? We need to go to the left. So again, because of x change x, we say set the start node, set my node's left child to the result of the recursive call to add. Well, what are you going to call it with? The same data, but you're going to call it with start node.left because you're following the left child. That might return something new, so you need to reassign it when it comes back. X equals change x. Else, it must be the right child. So all of this makes sense, but that assumes that you understand what's going on with x change x and the recursion stuff that we've talked about. So we're basing this on a lot of previous information. Let's go quickly look at the code for add. This should look very familiar given what we know. The client code facing public method where they just give us the data. We're going to call the recursive one starting at the root, and because of x equals change x, we're going to reassign root when it comes back. Now in a lot of cases, root's pointing to the same thing. Oh well, we're pointing it to the same object, no problem, right? It's just an assignment in memory, not that big a deal. And then here is our recursive code. If you go match this up with the pseudocode on the slide, you'll see that this should make perfectly good sense. The only difference is, well, yeah, it's just a little more technical, right? A little more Java implementation. If it's null, make the node, point to it. If the data is less than my data, reassign my left child to be the recursive call, pass the data, pass my left child as a starting point, remap it because of x equals change x, remap the right child similarly if the data is bigger, and return the start node because that's going to be required for the x change x universe. Hopefully that all makes sense to you. Now we're going to look at several more algorithms. We're going to look at how you can load data into the tree. Turns out that's awfully easy now that we have add, right? Trivial. And then we're going to look at a couple more to make sure that we're really getting this recursive algorithm thing down. The recursion is very elegant and beautiful, but it does take a bit to understand how exactly it works. So hopefully you're getting it as we go along here. Thanks for watching this video. Come back and we'll talk about contains, we'll talk about loading from file, and some other fun tree things. And then later we'll get into even slightly more interesting algorithms like delete, right? That takes some special thinking. Thanks for watching.